So in today's lecture, we are going for what is actually paging. For that purpose, page replacement algorithms are used, and segmentation. So in segmentation, divide the memory into the segment. So what is actually paging? How paging is carried out? Physical memory we have to specify using logical memory. So topics to be covered: paging and segmentation. So first one, what is the definition of paging, or what is actually paging? It is a memory management techniques that permits the physical address space of a process to be non-contiguous. Means what happens here? Whichever page you want to place in a physical memory, into the physical memory, that should be non-continuous. Means we can place any page anywhere in a main memory. Okay. So these are some basic definition. Physical memory is divided into fixed size block called as a frame. So your physical memory will consist of your frame in which we have to place the pages. Logical memory is divided into blocks of same size called as a pages. So what is this pages? Pages is a logical memory and your frames are the physical memory. So we have to place this logical memory into the physical memory. Means conversion of logical memory into the physical memory. That is done with the help of paging. A frame has same size as a page is placed where logical page can be physically placed. So whether you want to place that page in a physical memory, with the help of frame, we can place that page into the frame in paging. So address mapping, listen this is your process logical memory in which there are pages. Page 1, 2, number of pages are there. So in Windows, we are having the 4 KB size. Page size is how much? 4 KB. So this is page 1, page 2. So number of pages can place in a logical memory. And we have to place these pages into the memory. So what is there in physical memory? There are frames are there. What are there? Frames are there, which is same size of your page. Means 4 KB, 4 KB frame size. So this is called as a address mapping. Means we are placing the pages into the physical memory into the frame. Now how these pages are translated to the physical memory from the logical memory, or logical organization to physical organization. So we are getting what? We will get the logical address of that page. So whatever may be the logical address, so it will place into the memory management unit. So that is by the CPU processor will get this logical address of the page, and then it will place into the physical address or convert into the physical address. So there is a process of conversion, logical address to the physical address. There is a process, that is a page will be there. So this is how translation are done. Logical address to the physical help of CPU or with the help of processor. So this is your page. This is what happens here. We are converting the logical address into the physical address. Now listen here. Every address generated by the CPU is divided into two parts. First one is your page number, and second one is a page offset. So what is the page number? Each and every page will have the page number from the page table. So that page number and page table will consist of your pages and number. So use page number. So what is it? P, and offset is page offset is your D. So use as an index into the page table which contains base address of each page in a physical memory. Okay, what will the page number? It is an index in a page table which will consist of your base address, means address of your physical memory where we have to place that page. That will be the page number. So it will have the address. And second one is a page offset. So that is your D. So page offset D combined with the page address, so your page address, to define the physical memory address that is sent to the memory unit. Okay. So how much that size will be there of that page? So that will be consist of your page offset. So this is the structure, page number P, and D will be the page offset. Have you got this? So page offset is what? It is a combined with the base address of your page. That will combine with the page number, and that we are storing into the physical memory. So for given logical address space 2 raised to m and page size is 2 raised to n. So this is what page number m minus n means you are subtracting the that offset. So find the page number. Okay. So paging hardware, a page number is used as an index into the page table. So you are having what? Page number in a page table. The page size is defined by the hardware. It may be 4 KB, 8 KB based on your hardware. The size of page is typically a power of 2. So in Windows, I specify that is what? 4. 2 raised to 2, 4. Varying between 512 bytes and 16 MB per pages. So that will be the size. Reason, if the size of logical address is 2 raised to m and page size is 2 raised to n, then the higher order m minus n bits of logical address designate the page number. So that will specify the page number. So now this is a hardware for paging. So what is actually in this hardware? This is your CPU that will generate the logical address. This is your CPU. So logical address will consist of your page number. So that page number is from the page table, and that D is your offset address. Okay. So here we are getting the page number, and here is your EF, means what? Frame, in which frame you have to place. So these are the pages. So here page table will consist of your frame. So logical address. So again here you will get the offset. D is a offset for physical address, and from here we will get the frame where we have to place that page. Okay, and then it will give the address in a physical memory where we have to place that page. So this will get whatever address we will get here, in that with the help of that address, the page will be placed in a frame of the physical memory. So this is called as a paging. A paging example, when we use a physical paging scheme, we have no external fragmentation. Any free frame can be allocated to a process that need it. So there is no external fragmentation, which is there in a dynamic allocation. So that disadvantage of dynamic allocation is overcome in a paging. However, we may have internal fragmentation. Sometimes what happens, suppose your page is of 4 KB and your process is of 3 KB. Again, there will be a wastage of 1 KB. So that is a internal fragmentation, which happens in a paging. If the process requires n pages, at least n frames are required. That is necessary condition in paging. Suppose you are having 10 pages, so 10 frames should be there in a page table. That will specify the frame size, and then we can place into the physical memory. First page of process is loaded into the first frame listed on a free frame list, and the frame number is put into the page table. Okay, means that F will be placed into the page table, and from that page table we'll get the page number, and that frame will be placed into the physical memory. So here is your logical memory: page 0, page 1, page 2, and page 3. So there are 4 pages here, and now this is your page table. So how many it is? Again, it is having 4. So page number 0, page number 1, page number 2, and page number 3. So what is here now? Frame 1, 4, 3, 7. So what happens here? Page number 0 will consist of your page 0 in your frame number 1. Okay, page 0 will be where? Frame number 1. Likewise here, page 0 in frame number 1. So what is here? Here you will get the physical address. Means here we are combining, this will be your frame number and you will get the offset address from the page. So we are combining that and we will get the physical address. So your page number 1 will be in the frame number 4. So here, page number 1 in frame number 4. Then page number 2 in frame number 3. Here, page number 2 in frame number 3. And last one is a page number 3 in frame number 7. So here is a 7. So this is how we are doing the paging. Now here again same, how to convert your page into the physical. So I'm in here free frame. So here is the pages, new process. How many process will consist of your 4 pages? Page 0, page 1, page 2 and page 3. So this is your process. Now we are specifying free frame list. So this is a free frame. So your 14, 13, 18, 20 and 15 are the free. And we have to place this process into that physical memory. So here new process, page table. So which are the free? Page number 13 was free. Okay. Frame number 13 was free, 14 is free, 18 is free, 15 is free, and 20 is free. So we are placing these pages 0, 1, 2, 3 in 13, 14, 18, and 20. Okay. So new process come page table. So that is page number, frame number 14, 13, 18, and 20. So 0, 1, 2, 3. So 14, then 13, 18, and last one is your 20. So we are placing this pages with the help of frames into the physical memory. So that is done in a paging. So implementing page table. So what is page table? Page table will consist of your number, page number and frame. So which frame that page will be placed. To implement the paging, the simplest method is to implement the page table as a set of registers. So with the help of registers, we are creating the page table. However, the size of register is limited and the size of page table is actually large. So if the process consists of 20 pages and register cannot store the 20 pages. So how to store that? Therefore, the page table is kept in a main memory. So we can replace that. So memory management, address, translation. So how that MMU means your memory management will translate the physiological address into the physical address. So here is what page number and here is your offset. So in the example, they will give the offset. So offset will be given and page number will be given. So we have to place only that page into the physical memory. So here is your CPU means your processor memory management unit. So we can get the page number here. Okay. Memory management unit will get the page number from the page table. So here is a page number and from page table it will get the page number. So here physical address. Now it is converting the logical address into the physical address. So frame number F. From where it gets the F, it gets it from the page table. Okay. So from here it will get the page number. From here it will get the offset address is given. So offset address D. So here it will combine and then it will find the frame. Then it will find that frame where we have to place that page. So which your frame number it will get. So here we are placing that page. So that is the memory address translation with the help of memory management unit. Now implementing paging with the help of translation look aside buffer, that is a TLB. If you want to access any location, we must first index into the page table. This requires at least one memory access. The standard solution is use a special small fast cache memory called as a translation look aside buffer. A small part of your memory is used, or associative memory, that is called as a TLB, for accessing this page table. So here it comes again, same. Listen here. So we are using here TLB for storage of this page table and frame page number information. So that is a translation look aside buffer. So logical address, so memory management unit, and here is a TLB, translation look aside. It is a buffer for storage. Okay, in a memory management unit you will get the TLB. So frame number, offset again. So search here. Now listen here. Page table, search page table only in TLB miss. Means what happens here? It will firstly find here translation look aside buffer, whether that page number with that frame is available in TLB. If it is not available, search page table only in TLB miss. Translation look aside buffer will not consist of that page, then it will search into the page table. Okay, so what happens here? Instead of searching every time in your page table, so we are having the TLB, that is use of translation look aside buffer, which is already with the CPU, memory management unit. So from only here, instead of going here in a page table, search it in the TLB. If it is not found in TLB, that page number is not found in TLB, so it will go in the page table, and from that it will take the page table, and then again convert the physical logical address into the physical address. Okay, so that is use of TLB. So if the page number is not in TLB, so that is what TLB means. A memory reference to the page table must be made. In addition, we add the page number and the frame number into TLB. If the TLB is already full, the OS must select one for replacement. Okay, so that is page replacement. Some TLB shows allows entries to be wired down, meaning that they cannot be removed. Some pages cannot be removed. That is called as a wire down. From the TLB, for example, kernel code. So kernel is the heart of operating system. So we cannot remove that pages of that kernel. The percentage of times the particular page number is found in TLN is called as a hit ratio. Means your TLB, it is a TLB. So whatever we find that pages in your TLB only, so that is called as a hit ratio. And if that page is not available in TLB, that is a miss ratio, or then we are going for the page table. If it takes 20 nanoseconds to search the TLB and 100 nanoseconds to access the memory, so how much it is? Less time is required to search that page in a TLB instead of going a page table. So 100 nanoseconds for accessing from the memory and 20 nanoseconds only for accessing in a TLB. So what are the advantages of paging? There is no external fragmentation. So there will be no need of compaction. So overhead will be reduced. Simple memory management algorithm. Swapping is easy, equal size pages and page frame. So swapping, so whatever page we are putting into that frame, so that is the swapping is simple. Share common code, especially in time sharing environment. Disadvantages, internal fragmentation is there. Suppose your process size is 2 KB and your page size is 4 KB. So there will be the 2 KB wastage. So that is the internal fragmentation. So that is the disadvantage of paging. Page table may consume more memory. So we have to create the page table that will consist of page number and frame number. So this will require more memory. Multi-level paging leads to memory reference overhead. So means suppose you have page tables, so that will have the second reference. So this will lead to the overhead. Multi-level paging will lead to the overhead. Okay. So any difficulty here for paging?
No, sir.
Okay, the simple one. So that is called as a paging. Okay. Now second part is your segmentation. Now again in this segmentation, unequal size. Paging is has equal size, segmentation will have unequal size. Any size of segment you can create, and again here segment table. This will consist of your segment table, segment number. It is opposite of pages now. Instead of pages, we are going for the segment. So segmentation. So there is another way in which addressable memory can be subdivided, known as a segmentation or segment. We can divide into segment. So how does user view the memory? An important part of memory management that becomes unavoidable with paging is the separation of user view of memory and the actual physical memory. The user view is mapped to the physical memory. So actually logical address, user view, logical address is mapped into the physical memory. Thus the differentiation comes between the logical and physical memory. So do user view memory as a linear array of bytes, some containing instruction and other containing data? No, rather they would see it a collection of segment only. So this is your logical address space. So segmentation. So what is there? Subroutines are there, stacks are there, symbol table is there, main program is there, then your square root, whatever may be operation. So logical address space. The user view of logical memory. Linear array of byte reflected by paging memory scheme, the collection of variable size entities. So what is here? Segmentation of variable size entities. User thinks in the terms of subroutine, stats, symbol table, main program, which are somehow located somewhere in a memory. Segmentation supports this user view. The logical address space is a collection of segment. So these different types of 5 segments will be collected into the single one. So user feel only one. Segmentation. Although the user can refer to objects in a program by 2-dimensional address, the actual physical address is 1-dimensional sequence. Thus, we need to map the segment number. This mapping is effected by the segment table. So in paging, we are getting the page table. In segment, we are having the segment table. In order to protect the memory space, each entry in segment table has segment base and segment limit. That will give the size of that segment using segment base and segment limit. So here, logical address in segmentation. So this is logical address will consist of your segment number and offset, same as your page. So logical physical, in logical address in paging, it was consisting of your page number. So here it is segment number and offset. The mapping of logical address to physical address is done with the help of segment table. Is done with the help of segment table. So segment table will consist of your segment limit, segment base, and other bits. So whatever may be the other bits for specifying the segment. So segment limit, the length of the segment. So what should be size of that segment? Segment base, starting address of corresponding segment in main memory. It will give the starting address of segment in main memory. And segment limit, so it will specify the size of that segment. Other bits, a bit is needed to determine if the segment is already in main memory. Another bit is needed to determine if the segment has been modified since it was loaded into the main memory. So this is P and EM, whether that is available in memory, main memory, or it has been modified and then placed into the main memory. So the bit will say P and EM. About the segment table, segment limit, size, and base address, and other bits. Other bits are not important, but these two, segment limit and segment base, are required because we have to find the physical address of that memory for that segment. For this purpose, we require the segment table.